Hello everyone, today I'm going back to slightly more theoretical engineering and talk about the impact that reducing the amount of gravity you are going to create would have on the design and the feasibility of ring or wheel or tube-like spinning artificial gravity stations or spaceships. Now, I recently got to ask Charles Duke, a moonwalking Apollo astronaut, a question, and the video on that should be linked somewhere. And yes, that is somewhat related with today's topic, because being exposed to less than Earth gravity is actually quite a rare experience. We cannot really simulate less than Earth gravity on Earth. You can do parabola flights that can simulate 0 g and also anywhere between 0 and 1 g, but these usually only last for a few seconds, and of course we have the International Space Station, and we have not that much but quite a bit of research into zero gravity and the effects that has on everyday life and human health. But most astronauts only ever get exposed to 0 g for a longer period of time, which is of course really interesting, but when it comes to anywhere between 0 g and 1 g, then only the Apollo moonwalkers actually got exposed to somewhere between 0 g and 1 g for more than a few minutes at a time, and actually got to walk around and do work under such conditions. And so this is actually quite a rare experience. And that's kind of important because, well, we're currently having lots of, at this point, still theoretical but maybe soon practical ideas about sending humans to other planets, sending humans to the moon again, sending humans to Mars for a long period of time, of course, because you can't really go to Mars and back for just a few days. And also we have ideas for building spaceships that would create artificial gravity by having a tube or ring or module that is spinning like a centrifuge, using centrifugal force for artificial gravity. Now for the length of this video, let's just say centrifugal force is an actual force, because there tends to come up a lot of discussion on the internet if centrifugal force is actually a force, it's only an apparent force, and then it gets confused with centripetal force, and you could make another video about this. I might at some point make another video about this, but then it has also been discussed before, and it is actually a relatively basic question, but it does get a bit complicated if you want to talk it all the way through. So for now, let's just say centrifugal force, for all intents and purposes for this video, is an actual force, and it does more or less replace gravity. And then there are of course some really far out ideas about building gigantic rotating habitats and such, and of course for the far future, when we're much more technologically advanced, it might be practical to build such habitats for the amount of artificial gravity that we find most practical or most comfortable. But then when you look at the nearer future, it would seem that our designs for such rotating artificial gravity devices would be rather limited by our engineering capabilities and by our capabilities of what we can send into orbit, what we can afford to send into space, and what we can build in space. A gravitational force or a fake gravity of less than 1 g is already a great step of progress. You can watch Charles Duke's response to my question, of course, but just to bring in the basic idea, Of course, it's not the same as 1G, and you will still have to do exercise because it will still impact human health, and we don't know exactly how, but it seems likely that much less than 1G, say lunar level gravity, would still be much better for human health than 0G, and it's a lot more practical. It seems much easier to exercise by just walking around carrying heavy weights than by strapping yourself down to some weird exercising contraption. And everyday life seems much more practical and also much more safe on board of a spacecraft. You could just put things down on a table and expect to find them roughly where you put them down when you look back again, instead of having to expect them to float away. You can operate with small powders or dust, like, for example, graphite from a pencil, or metal powder for a 3D printing device, without having to be scared of that dust or powder floating away, floating somewhere into electronic devices, causing short circuits, causing fires and such. You can just walk around and sit down and have a relatively normal, relatively practical everyday life. You can use most devices like on Earth. You can probably sleep in a bed without having to strap yourself down, because astronauts can't really sleep that easily because they have that constant feeling of free fall, and the human body is instinctively programmed to instantly wake up if it is asleep and feels like it's falling. It instantly wakes back up, so the astronauts have to strap themselves down currently on the ISS in order to be able to sleep, so they have that feeling of pressure against their back, so they feel tightly secured, so they don't instantly wake back up as soon as they fall asleep. So it seems much more practical to, for example, build a rotating habitat or a artificial gravity device with, say, lunar level gravity rather than Earth gravity. It's still enough to be very helpful on a long journey, but it's much less expensive. And now I can run the rough numbers for how much less expensive this might be. And it actually doesn't scale proportionally, it scales a lot more extreme. So, of course, for starters, we have less load on the material. If the artificial gravity we create is only lunar level gravity, then that means that only lunar level gravity is pulling at the structure at the end of this artificial gravity device, is pulling on the actual payload, and so we have less force to deal with. We need a thinner or less structural material to actually keep the whole thing from tearing itself apart. But that's not all. In addition, we can also build our rotating space station a lot smaller now, because there is a limit to how small you can build a station. Uh, that is again a rather complicated topic, but basically there's a maximum to how many rotations per minute you want it to take, because humans get nauseous if you spin them quickly. So generally it's often accepted that around 2 RPM are a rough idea for that limit, and that would mean that a station with 1G artificial gravity would need a diameter of 450 meters, which at our current technology would be incredibly expensive to build. But at the same RPM, the same rotations per minute, the diameter you need is proportional to the gravity you want to create. So for lunar level gravity, you would only need a station 1/6 that diameter, which means that you only have to support the load of the artificial weight of your payload over a shorter distance. Now, scaling can also get a bit complicated, but basically it's the square cube law that if you support a weight over a shorter distance, you also save structural mass. So here again you again save a factor of 6, so now we're at 1/36th the structural mass or the material strain we have compared to a 1G station. In addition, we also get it down to a size that we are relatively comfortable to build in. 75 meters is still relatively big, but we have built airplanes around that order of size. We have built rockets that are larger than this. The ISS is larger than this, but that of course is completely zero gravity. And I think you could make it even smaller. You could get away with a little less than lunar gravity. You might get away with a little more than 2 rounds per minute. So you could get this down to a relatively sane and practical size that we could build within the near future. For example, if you would double the RPM, you would actually get 4 times as much gravity, or the same gravity at 1/4 the diameter. And of course, if you have a relatively heavy payload anyways in the center and you only have a habitat module attached with a tether rotating around it, the structure you're building is only actually the radius in size, so you could get this down to sizes that we are quite comfortable building spacecraft at, or building even spacecraft that re-enter and land and get exposed to gravitational forces. And compared to a larger ring station that would provide Earth-level gravity, this is a lot cheaper, depending on if you see it from an optimistic or pessimistic perspective, and of course which way around you define optimistic or pessimistic. But it could be somewhere between 10 and 200 times cheaper than a 1G station. And for small crews you would easily need less than 1/100th the structural material. So this actually means that it might be feasible to travel to Mars under artificial gravity. For example, there have actually been some theoretical studies done before, although that were designs that would actually create more than lunar level gravity, where you would have a Mars mission with a space capsule serving as the habitat and command module, and that would be tethered to a used up or still active stage of the rocket launching it, and the whole thing would be spun up around that tether using RCS thrusters, and then you would have artificial gravity because those would spin around their center of gravity, and the capsule would hang from that tether under centrifugal force. And that would get a lot easier, of course, if you would only create lunar level gravity. In fact, if you go a little below lunar level and a little bit above 2 RPM, you might even be able to create a sort of artificial gravity centrifuge that you could completely enclose within a space capsule or spacecraft and carry around with you, although that would not really be very practical. Either way, I think this is quite an interesting and important topic to think about. There might be more and more detailed stuff coming from me about this, and I'm very grateful that I could ask my question to Charles Duke at the Spaceflight Conference in Germany a few days ago. I hope you enjoyed this kind of long-wound introduction to the idea of scaling down ring stations or artificial gravity devices. And as always, thanks for watching.